Over 35% of all Internet-exposed OpenClaw deployments are vulnerable to complete host compromise. That metric comes directly from SecurityScorecard's recent strike research, mapping tens of thousands of unique IPs operating with exposed control panels. This chart tracks the sheer volume of OpenClaw's adoption, reaching 327,000 stars and 63,000 forks on its main repository. The ecosystem has scaled so fast that opportunistic abuse campaigns are now targeting its default settings. The exposure is severe enough that China's National Cybersecurity Center, CNCERT/CC, issued a highly specific public risk notice detailing exact exploitation patterns for the platform. The root cause lies in user behavior. Developers are taking one-click VPS templates, configurations designed strictly for local, isolated experimentation, and pushing them directly to the public internet to save time. This risk profile has nothing to do with artificial intelligence making autonomous, hostile decisions. It is a mathematically verifiable crisis caused by exposing highly privileged local developer tools to a hostile network environment. OpenClaw's official security documentation defines a very specific baseline trust model. The platform assumes a deployment has exactly one trusted operator, sharing a single gateway boundary. The platform does not claim to provide hostile multi-tenant isolation out of the box. It is built to execute commands, not to defend against the person giving them. The default onboarding experience is intentionally frictionless. A user spins up a gateway on port 18789, opens a browser-based dashboard, and the system connects immediately without enforcing authentication layers or access policies. This node graph maps out that frictionless state. The agent runtime connects directly to host functions, tools, skills, memory, with zero structural shielding. Treating this local framework like a public bot exposes an undefended attack surface where compromised inputs cascade directly to the operating system. An architecture optimized for developer convenience fails under adversarial pressure. To secure OpenClaw for production, we have to dismantle its default state and rebuild the platform from first principles. The first vulnerability trap is default credential exposure. By default, plaintext secret values and API keys are left resting on disk in files like openclaw.json and your environment file. If an attacker crosses a tool boundary, they do not need complex exploits. Their immediate next step is executing a simple command to read local files or dump environment variables, instantly capturing your infrastructure keys. The required architectural fix is migrating all static credentials to dynamic SecretRefs. A SecretRef is a configuration method that securely pulls credential values into memory exactly when needed, rather than storing them in hard-coded text files. This diagram visualizes the structural fix. Running OpenClaw secrets configure strips static credentials from configuration files, replacing them with runtime resolved in-memory snapshots. Passing the secrets audit-check command must become a mandatory automated gate, preventing plaintext material from reaching production. Securing secrets in memory ensures that even if an agent is compromised, the attacker cannot easily pivot into your broader cloud infrastructure. The next trap is indirect prompt injection. Attackers do not need direct access to the bot's chat interface. They can poison the agent through untrusted data, like fetched web pages, like incoming emails, or pasted logs. There is zero mathematical separation between trusted developer instructions and untrusted data fetched by the tools. The data itself becomes the malicious instructions. This injection flaw multiplies when combined with agent memory. OpenClaw stores its long-term memory as plain markdown files, specifically memory.md, saved directly to the agent's workspace. Because this memory file is injected into the context window on every single turn, an injected prompt can instruct the agent to write a persistent backdoor to disk. That backdoor survives across user sessions and system reboots. You cannot reliably filter LLM outputs after the fact. The structural mitigation is role splitting, deploying a read-only, sandboxed agent specifically to ingest and summarize untrusted content before it ever touches your core agent's memory. System prompts are purely advisory, not deterministic. The only way to prevent data exfiltration is to physically isolate untrusted data ingestion from your persistent memory writing processes. We also have to address ClawHub, OpenClaw's public skill registry. It is designed for frictionless installation of third-party capabilities, pulling down folders centered entirely on a single skill.md file. recent audits by SNCC and COI Security revealed hundreds of malicious skills active in the registry, explicitly designed to distribute credential-stealing malware and install proxy backdoors. This supply chain threat is severe because installed skills inherently operate with the exact same host-level privileges as the core agent itself. If the agent can read your files, the malicious skill can too. Your defensive posture must explicit default deny all external skills in production. You must force the gateway to pull only from internally mirrored, explicitly approved code bundles. Allowing auto-updating plugins in an AI ecosystem is equivalent to handing untrusted third parties arbitrary code execution rights on your servers. The urgency of these architectural flaws is proven by CVE 2026-25253, a severe vulnerability found in OpenClaw's default control UI. The attack path was entirely automated. The UI trusted a gateway URL query parameter, established a connection, and blindly sent an authentication token through a WebSocket. A WebSocket maintains a continuous connection between a client and server, allowing the attacker a direct pipeline into the system. Once the token was exfiltrated, attackers pivoted to remote code execution. They succeeded because the platform's exec tool was left running directly on the gateway host, without containment. Remediation requires patching past version 2026.1.29 and binding the gateway strictly to the loopback address. The loopback address is a localized IP that only allows a computer to communicate with itself, completely physically severing all external network connections. Furthermore, you must entirely eliminate identity sprawl. Each agent requires its own isolated, managed identity, provisioned with least privilege tool profiles to tightly contain the blast radius of a compromised session. Exposing an administration control plane without robust network sandboxing guarantees that a single software flaw will cascade into a total loss of infrastructure control. This is the fully rebuilt, secure OpenClaw gateway. The core agent is encased behind strict ingress controls, proxy layers, and deterministic execution boundaries. The vital control is Docker sandboxing. Dropping Linux capabilities and setting network policy to none completely deflects malicious code execution. The tool proxy enforces hard deny by default logic and requires explicit execution approvals before the LLM is ever allowed to process the incoming data. True security is achieved by removing decision-making power from the AI model entirely and placing it into inflexible, deterministic network infrastructure. The cybersecurity industry relies heavily on the assumption that writing a strict system prompt will govern an AI's behavior. That assumption is false. OpenClaw's own documentation explicitly warns that system prompts are merely advisory. Actual enforcement requires continuous validation using rigorous tools like the OpenClaw Security Audit Deep Command. If an agent processes untrusted external data and possesses unrestricted execution rights on your host machine, it is essentially dormant malware waiting for a trigger. The era of defaults that work fine is over. To survive the hostile environment of the public internet, engineers must architect the cage before they ever activate the agent.